Hi everyone. Today I'm going to be talking about gravitational fields. This is lesson 1 for chapter 18 basically. So it's the first lesson I'm going to start on gravitational fields. I'm going to be looking at what causes gravitational fields. We will also look at spherical objects as point masses at their center, and I will explain that as we go through it. We will talk about the gravitational field lines and how to draw them, what gravitational field strength is and how what is defined as and how to calculate it, and basically how gravitational fields are one of the forms of a field giving rise to a force. This is a wide topic. It covers a lot of concepts. But these are the first things we're going to see in the first half of the lesson, and then I will go on to the other bits later when we start looking at them. So to start with, what are gravitational fields? Why are there gravitational fields? Well, all objects that have mass have a gravitational field around them, including yourselves, including your laptop or your book. Anything that's made of matter, which is everything that you can visibly see around you, at least, have mass, and they all have a gravitational field around them. Obviously, the bigger the mass, the stronger the gravitational field around an object, and it always all this gravitational field around us and the Earth and anything that has mass extends to infinity. But obviously, it will get weaker the further you are from the mass. So my gravitational field strength outside the house is less than my gravitational field right next to my body. You do need to know the definition of it. This is actually, if you learn the definition of one of the fields properly, then it will make sense for the rest of the fields as well. So if you do have an object, so a mass, let's say it's a ball, we have a ball, and I want to define what gravitational field is around it, is the area around a mass, where if I placed another mass, so if this is mass m, if I placed a little mass near it, small m, it will experience an attractive force towards the center of the mass of the object, creating it. So in other words, any mass has a field around it, which is an area that if I place another mass, it will experience an attractive gravitational force because of the mass that created it, due to the mass that created that force. Obviously, you'll think, but if this is a big mass that has a gravitational field around it, then surely this mass has a gravitational field around it. Yes, it does have a gravitational field around it, but objects tend to move from bigger, smaller objects tend to get attracted to bigger masses, as their field strength is not as big as the bigger mass. This is a good topic to consider the synoptic links. So gravitational force is something that's a non-contact force. We will also be applying Newton's laws of motions here as well, which is quite a very synoptic link to a lot of topics actually. But yeah, gravitational force is a non-contact force, so it means that the objects don't need to be near each other to experience that force, or touching each other for that matter to be experiencing that force. But they always do. So the Earth and the Moon, or the Earth and the Sun, they're not close to each other or touching each other, yet again they're attracting each other. So that's the idea behind non-contact forces. So let's go first to define what a gravitational field strength is. Now, we define it as the force exerted per unit mass at that point within the field. So if I placed so if this is the Earth, and I placed a little mass near it, then the gravitational field strength at this point exactly will be the force exerted per unit mass on the small object placed at that point within that field. It is a vector quantity as it's relying on force, and force is a vector quantity. So it means it has a magnitude, so a size, and it has a direction. And it always points towards the center of the mass of the object, creating that gravitational field strength. Now, if I want to write my equation based on the definition, let's go up again. It's the force exerted per unit mass. So gravitational field strength is force per unit mass. That gives us units of newtons. This has units of kilograms. That means we have Newton, sorry, I'll write it here. That means G, the gravitational field strength, is newtons per kilogram. Where F stands for the gravitational force, M is the mass of the object in the gravitational field, and G stands for the gravitational field strength. Now, can we think how this can be similar and different to an electric and magnetic field? Well, first things first, gravitational force is always attractive. There is no repulsion. So you can, for example, the Earth attracts the moon. It doesn't repel it. No masses repel other masses. They always attract them. If you do want to read a little bit more into what is going on, or how that might be different with different theories, Einstein's general theory of relativity actually looks into this space-time fabric. I would suggest you have a quick view on YouTube videos that talk about Einstein's general theory of relativity. It is quite interesting, but obviously for the course we don't have to go through it, and I'd rather keep the videos as short as possible. So I won't go through it now, but it's quite a nice concept to have a look at. So gravitational force is always attractive. So how is that different to electric and magnetic fields? Well, we know that magnets, if I had the south and south of a magnet, they will repel. With masses, that doesn't happen. There's no negative or positive or south and north part to a mass. They're always attracting. Also, if I think about how this equation for an electric field and a magnetic field should be, well, it will be the force experienced by, in the case of electric charge. So this is the electric field strength. It will be the force experienced per unit charge, because we're talking about charges. And for magnetic fields, how do you think that should be? Since with magnetic fields we don't have unit charges or unit masses, it varies a bit. So it doesn't follow quite a similar equation, because it depends on whether it's a wire creating the magnetic field or whether it's a charge moving in a magnetic field. The equation differs. But yeah, I'll just leave it to that for now with the electric and magnetic fields. But this topic, gravitational fields, electric fields and magnetic fields, are very well linked together, and it's a good idea to keep in mind how that will be different for electric and magnetic fields until we come to it in the next chapters I will be teaching you. So let's move on to the next part. Now you are all used to these equations. So F is equal to ma, and for weight in particular, so when we talk about gravitational force on Earth, is basically the weight of each object. So every object will experience a gravitational attraction to the Earth, and when we talk about gravitational force, we usually refer to weight. So you can see that if we compare F is equal to ma and F is equal to mg, where here is the resultant force, this is the mass of an object, and this is the acceleration of an object. Now if we consider an object falling under free fall, meaning there's no air resistance or anything to slow down the object, we know that the acceleration of free fall is 9.81 meters per second squared. Sorry, that should be an A, because we're talking about acceleration of free fall. When we talk about calculating weight, we talk about the mass in a gravitational field strength, and we usually give it as this unit of it as newtons per kilogram. So if we compare the two, well, the gravitational field strength at a point is also equal to the acceleration, because the equations are the same. This value, this is the force that we're talking about. Mass could be the same mass of the same object. So the gravitational field strength at the point is equal to the acceleration of free fall at that point. So that was just a little comparison to remind you of a few things that you already know. Then we have the concept about representing gravitational fields. Now, gravitational fields can be represented using lines, gravitational field lines. Do not confuse them with forces. When we draw gravitational field lines, is the area, like obviously when you look at this diagram here, before I mix myself up and yourselves up, when you look at this diagram of the Earth, these black lines show the gravitational field lines. Obviously, there's no such thing in the world where you see lines coming into the Earth. It's simply how we represent it, how we can show the gravitational field strength around the Earth. And there should be in reality infinite lines around it, because it doesn't stop here in the middle. There is gravitational field strength, gravitational field right there as well. But we usually represent them to make things simpler for us. So if I drew more lines in this diagram, that will mean that the field strength is stronger. So first things first, there's some rules to follow. They never cross each other. The arrows need to show the direction of the field. Now, because we're talking about gravitational field lines, they're always attractive. So they always point towards the center of the Earth. So if this is the center of the Earth, if I continue the lines, you can see they're all passing right through the center of the Earth. Stronger field is shown by more lines closer together. That's why we don't draw infinite lines. So if I wanted to show a stronger field, I will have to draw more lines. So you can see that at this point now I have more lines per unit area, or if I wanted to look at it in a 3D perspective, because these are 3D, these are all around the Earth, then that will be, you can see there's more lines with the added red lines I added. There's more lines per unit area compared to this section, for example. And also you can notice that when it comes to point masses, so if, by the way, a point mass is a very, very tiny amount of mass, or some mass concentrated, or all the mass, of an object concentrated in one tiny little spot. So when we talk about point masses, all the field lines will be in every direction. Sorry, my drawings are not that perfect, but hopefully you can see through them and understand. So you can see that the Earth is not obviously a point mass. The Earth is quite big. It has quite a big volume. And when we do questions and when we analyze questions in physics, we tend to consider that all of its mass is concentrated right at the center. Since it's an attractive field, it will always point towards the mass that's causing the field. The bigger field anyway. So stronger fields are shown by more lines. Radial fields is what every point mass will have, or Earth, or the Moon, or the Sun. The strength does decrease with distance from the center. So you can notice that, for example, here the lines are closer together, but here they're more spread away from each other, which means that a mass here will experience a smaller force per unit mass. And then we have uniform gravitational field. This is what we see at the very point of sea level, at the sea level of the Earth. So you see in this diagram here, you can see the person standing, and the field lines are all parallel to each other. They're not crossing each other. They're not similar to the radial field. So if I zoomed very closely at the Earth, there is a very small difference between the gravitational fields. So we will assume and take it that the gravitational field is very uniform on the Earth's level, and we can represent it by parallel lines, but they also have to be the same distance. So if this is 1 centimeter, this should also be 1 centimeter. If they're not equal distance from each other, obviously it can be, you're showing that it's a stronger field. Let's say if I had another line here, it's like me saying that there's a stronger field here than there is here, and that means that it's a non-uniform field. So spherical objects have radial fields around them, which is not uniform. So if you move from one point to another, from let's say here to here, then you don't have the same gravitational field strength. These yellow lines, by the way, represent points around the Earth that you will experience the same exact force per unit mass. But obviously, if you go from this line here, so this line to this one, then obviously you'll have different force per unit mass. It will be a bigger force per unit mass because it's closer to the Earth. So as a general rule, these lines are all imaginary. The yellow lines, we call them equipotential lines. They simply show lines of equal field strength. But it's not a big requirement for you to know this for the course, but it's useful to understand because it will help us later on when we want to look at different energies at different points that you need to move someone through. So I'm going to move on to show you quickly how the lines change. So if this was a point mass right here, these green lines that you see are the field lines in 3D. Obviously, they're supposed to be in all directions around, but this is just for one section. And you can see that they're much closer together near the mass. And as you go further and further and further away from the point mass, these field lines are spreading further away from each other, which means that your field strength decreases, and they spread even further and further as you move away from it. So it is an infinite field, but its strength decreases by a lot each time. And we're going to look at the relationship that force has with distance from its center. So I'll start on to that. Okay, just to recap, before we move on to the next part, gravitational fields are due to objects having mass. So like I said, your cells are attracting every other mass around you. Modeling the mass of a spherical object as a point mass at its center. So if you have a big object, you consider that all of its mass is at its center. Gravitational field lines to map gravitational fields. Just to remind you that gravitational fields are also vector quantities since they have a direction and a size as the same as gravitational field strength, sorry. And the concept of gravitational fields as being one of a number of forms of fields giving rise to force. We did briefly discuss this in terms of electric and magnetic fields around, charges or magnets individually. So yeah, we're going to move now to the next things that you need to know. You should be able to demonstrate and apply knowledge and understanding of Newton's law of gravitation. This equation is given to you, so you don't have to memorize any of it. But you do need to be able to state Newton's law properly. There are key terms that need to be included. Then the gravitational field strength for a point mass, so for a radial field basically, and the gravitational field strength in uniform close to the surface of the Earth and numerically equal to the acceleration of free fall. So it's something that we already kind of discussed here, but we'll talk a little bit more about it. So Newton's law of gravitation is used to describe the forces acting between any objects that have mass. It's a very fundamental law, and we use it for a lot of things, including analyzing planetary motion, and we will see that in later chapters. But the idea is that since each object creates its own gravitational field, then the interaction of this field gives rise to forces between the objects. So we start with looking at this image here. Sorry, let me pen. So if we look at this image here, we have 2 point masses, point mass M capital and then point mass lowercase m. Due to the fact that they both have gravitational fields, those gravitational fields interact and they give rise to a force. You already have learned from Newton's third law of motion, so that any action has an equal and opposite reaction. So what you have is the bigger mass m is attracting smaller mass m, but the small mass m, so the lowercase m, is attracting the so you can see, once again, sorry, I'll use a diagram. So big M attracts small m, so this force here is that attraction, and then small m attracts big M, and you can see this force as well. This is because of Newton's third law. So an object will experience a force, the other object will experience an equal and opposite direction force. So action, a reaction, remember that, Newton's third law. And if we put it in real objects, like for example the Earth and the Moon, so if this is Earth and this is the Moon, then the force experienced by the Moon due to the Earth is the same as the force experienced by the Earth due to the Moon, but in the opposite direction. So the same type of force is the same size, but it's in the opposite directions. The only thing is that it acts on different objects. So remember that about Newton's law, Newton's third law. There's 3 features of Newton's third law, is that the same size force, same type, opposite direction, but acts on different objects. That's, sorry, four key points about it. Now the law, the actual law. Newton discovered that the force between 2 point masses is directly proportional to the product of their masses. So what you see here, the product is by multiplying them, capital M and lowercase m, but it's inversely proportional to the square of their separation. So if I combine these two, it's going to be m over r squared. And then we can rewrite the equation with a constant. In this case, the constant is the gravitational constant, the capital G. And the minus sign is also very important because it shows that this is an attractive force. Now the value of G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram to the minus 2, or per kilogram squared. We can prove the units as well. It's quite easy to do by rearranging for G. So if I rearrange for G, it will be F R squared over mm. So you can see is newtons meters squared, and then kilogram, then that's kilogram to the minus 2. Okay, so this is the mathematical expression. You do need to know how to define Newton's law of gravitation. It's a very fundamental law, so it's very, very important. So the force between two point masses. So if you remember, if you remember to link that this is the actual law, you can come up with the expression quite quickly. So it's going to be the force is directly proportional to the product of the masses and inversely proportional to the square of their separation. So just by using the equation, you can simply define it. It's quite a simple one. So now let's define each part of it. So this is the important part that many people get wrong in exam questions. This is their separation, not their radius, their separation. And you can see from the diagram that it's from the centers of the objects. So if they're not point masses. In this case, they're point masses. But in this example here, they're not point masses. So we need to assume that they're point masses and consider that all the mass is concentrated in the center. So we do need the radius. So if I have radius 1, and this is radius 2, then I will need the radii of the two spheres plus the distance between them to get the whole separation. So the whole separation is from their center. So that's a common mistake that many people forget and leave out. They think that r is the radius, or many people take the distance from one to the other without considering that they're not point masses. Then we have G, which is the gravitational constant. M and M stand for masses of objects that are causing the attraction between each other. And then F is the gravitational force that they will experience. Also a quick reminder that this stands for an attractive force. And both masses involved in that gravitational attraction will experience the same force but in opposite directions. So if one is pulling the other one with 100 newtons and the other one is pulling the first one with 100 newtons back. That's Newton's third law that we apply in a lot of different concepts. Now from the equation you can see that here, so this inversely squared proportionality between them, that if I doubled the distance, so if I doubled the separation, that will mean, actually let me write it nice and neater. So if I were to double the separation, then I'll come up with an expression that basically says that the force will decrease by a factor of 4. So the further you go away from a mass, you can see that the force experienced by the point mass that you place within that field the force will decrease depending on how far you go from it, but it decreases by a huge factor. So it's not just if I double the distance the force halves. It actually, because it's r squared, it will fall by 4 times. So that's a bigger difference. Now, obviously, you all know that this is not true for every single scenario. It's not just one object causing a force on another object. You might have a lot of objects in the, well, we do have a lot of objects that cause an attractive force on each other due to their masses. But when we analyze planetary motion and things like that, we definitely have more forces acting on objects. So if several objects are involved, then we need to determine the resultant force by adding vectors. If we're talking about one dimension, so for example, we have one object in the center, let's call this object B. There's one object here, let's call this object A, and then we have another object and call this C. Now, object B will experience a force due to object C. So it will be attracted to object C. If we consider the other force that object B will experience, it's an attraction to object A. But then object A is also attracted to object B by the same force. But it also gets attracted to object C all the way there. So that will be FAC. The same thing goes for object C. The object C will be attracted to object B by the same equal and opposite force that object B experiences from it. And it will also experience a force towards object A, which is equal and in opposite direction that A experiences too. So in this case, you will need to, for example, if you wanted to calculate the force on A, then the force on A will be the addition of the two forces acting on it, so FAB plus FAC. If you want to calculate the force on B, so this will be the resultant force, will be FAB. We're talking about object B, then the force on object B, the resultant force on object B, will be the force BC minus force of AB. By the way, I'm minusing it because I'm taking this direction to be positive, because I already took it to be positive for here. I will continue that standard of it. And I have to do it for all three objects in the same way. And then if we go to force on C, the resultant force on C, it will be, since they're in the opposite direction, will be minus FBC minus FAC. So that's just how you deal with one-dimensional diagrams. But if you had two dimensions, then you might need to use Pythagoras theorem or the sine and cosine rules. So this topic brings in a lot of Newton's laws and a lot of analysis of vectors, especially if you have to, if they're not at 90 degrees to each other. So you can't use Pythagoras theorem or sine or cosine rule. If you can't use Pythagoras theorem if they're not 90 degrees to each other, you can use a sine or cosine rule. You might need to resolve forces. It depends on what the question gives you, but all times you need to remember that Newton's third law is very important in this topic. So let's see, in this case, for example, if I had an object that so let's say we had objects that are that are 90 degrees to each other. So let's say all these planets were 90 degrees to each other. Then we will have object B experiencing a force. We'll have object B experiencing an attractive force towards A. It will also experience an attractive force towards C. But then also C experiences an attractive force towards the same one, BC. I will experience a force towards AC. now they all are experiencing a force due to each other. And in this case, if we focus just solely on B, for example, because B could be 90 degrees to each other. So if I took these two forces and this angle was 90 degrees, I could resolve it to find the answer. Alternatively, so the resultant force of it. Alternatively, you can do it for here as well and here as well. We will do examples in class though of this type of questions so you can experience it more. Just wanted to return back quickly to the things that we're learning. So we talked about Newton's law of gravitation. Now I do want us to discuss this part. This is an easier part to actually even have a look at because we already learned two equations that we can combine for it. So we said that the gravitational field strength is defined as the force experienced by point mass at that point where it's at per unit mass. So gravitational field strength is force per unit mass at a point in space. And we also learned that force in the radial field between 2 point masses is minus gmm over r squared. We talk about radial fields because radial fields don't have constant gravitational field strength, which means the gravitational field strength changes with distance. So that means that what we can do is substitute this expression into G. So we can find G, the gravitational field strength for a radial field. It's very important to understand that this is what we're going to show now is the gravitational field strength in a radial field, not in a uniform field, because obviously you wouldn't expect G to change in a uniform field. So I'll just substitute it in there. It's going to be minus gmm over r squared divided by m, which leads to, which I can cancel out the small m's, and it leads to an expression of minus gm over r squared. I think you're given all of this. Let me double check in the formula booklet. Remember that you're given all of these expressions, but you should be able to show how to get from one to the other. Yeah, you are given both expressions. Well, all the expressions we just came across so far. We have this expression. Again, the negative sign shows that the gravitational field strength at that point is in the opposite direction to the displacement from the center. So if this is the Earth and I want to know the gravitational field strength, here is basically showing to you that the field, which is always directed towards the center, is in the opposite displacement to the to the displacement r from the center of the mass. So the displacement is in this direction. But the force experience is in the opposite direction, so the gravitational field strength. The negative sign stands for that. Oh, sorry, negative sign here stands for that the field basically is an attractive field. So the same thing with the equation that we said before. So from this equation, you can see that the gravitational field strength at the point is directly proportional to the mass of the object creating the field. So once again, G is the gravitational constant. Capital M stands for the mass of the object creating the gravitational field. And it's inversely proportional to the square of the distance from the center of mass. So that's the distance from center of mass to that point in the field that we're looking for. So like the separation basically again. I will go through a graphical analysis in the next video. Just to wrap up though, before the video gets too long. The gravitational field strength is uniform close to the surface of the Earth, is what I've discussed already with you. So G for uniform field simply can be calculated using these values only. It's different for radial fields because the gravitational field strength changes with distance. So please make sure you separate uniform fields from radial fields, which will be useful as well when we have a look at electric fields as well. So ask me any questions that you have and we'll go through more questions in class.